But before we talk about hands-on cyber activities, we will be going through now a little bit of needs for modeling, right? So with that, let me share my slides. Can you see it okay?
Yes, sir. Yes, sir.
Yes.
Okay. So, like I said, that we are going to talk about integrated cyber physical modeling, and the part that relates to is more about cyber infrastructure and modeling part, right? So right here, this modeling. So again, going back to the cyber physical system modeling, we already have discussed about physical system, right? Which is dependent on our cyber, which is ICT, information and communication technology. SCADA, we talked about. EMS is also there. And when we think about modeling a test bed, it's all about how do I integrate ICT and power devices, right? While everything like communication delays is modeled, and also the two other things which we'll talk about later is the test bed of two different simulated system is synchronized somehow, right? Because the time is very important, and simulation depends on the time steps and time, right? So if you have done numerical simulation, you know that doesn't matter that what you choose, it's a MATLAB versus all the way till RTDS or OpenRT or Typhoon, which is very high resolution, small time scale test bed to larger system in offline mode, which is like analysis software. Every software has a time steps for calculating the numerical values for the next time step, and that's how you simulate the system. So it uses the system information and it generates the next time steps. Now the algorithm can be, or solver can be very, very different. So if you're solving the power flow kind of things, you're only looking at steady state behavior of this physical system, right? If you're doing the transient stability analysis, then you're looking at the transient and dynamic system behavior. For that, you need more data because you need a dynamic system state at each uh, generating plant and transmission line. If you don't have those data and you still want to do dynamic, you cannot do that, right? So unless we have a data for dynamic simulation, um, you cannot do the dynamic, kind of cyber physical simulation either. Cyber system is, is a data packets, right? With again sensing, computing, communication. So when we model that, you can model SCADA system, you can model EMS, right? And then other ICT devices, if you want to model, it becomes a little bit tricky, but sometimes we can model the behavior of communication delays. And we'll see that how to do that with multiple different examples before you go through one hands-on and more detail on one of the cyber simulator. So again, to set up the requirement, try to understand that in cyber system or physical system, when we want to make a test bed to validate our concept, it is important to first set your goals. What kind of behavior we are trying to model, number one, right? And you have to adjust your goal based on the data availability. Then second, what kind of solver or software I will use to model the physical system and to model the cyber system. Now, if you want to model the interaction between transmission and distribution, that is another interface, that how you can interface the TND, which, as it seems like, is also very tricky, that how to model the behavior of transmission and distribution interaction. If you only want to model a distribution system, of course, that's a little bit easier, depending upon that what kind of behavior we are trying to model. If you're trying to model the behavior of inverter-based switching, that is much more tougher at the system level compared to if you're trying to model the power. Okay. So with that in mind, the first thing is requirement. Next, if you want your cyber physical system model to also have a cyber security, it is a different, slightly different kind of modeling, because now you are trying to emulate or simulate vulnerability. Okay, and vulnerability does not exist in your simulation unless you tell it to. So vulnerability itself need to be modeled. You have to actually send some kind of you need to again set up your goal, that do you want to model the security defenses that already exist, like simple thing is like firewalls, which is a little bit easier to model compared to whitelisting, and which is allowing certain IP addresses, or blacklisting some IP address, which means that some other IP address are not allowed to access. Setting up this demilitarized zone or security perimeters, will be a little bit more tricky. I mean, all these are possible. How much detail you want is the question that you need to ask yourself when you are trying to model the cyber system together. So these things are basic, which does not guarantee cybersecurity. It is just blocking certain access. Misconfiguration, if you want to model, which can be done by a cyber attacker, that will require a little bit more detail. And then if you want to model the data flow from trusted versus untrusted resources, you need to actually have the emulator, because simulator will not work to send the information from one point to another point. Remote access point, again, you will need to do some kind of emulation or real hardware in the loop, so you can model all these different roles. And these roles are important because everyone has a different kind of access. Okay. If you want to model more detailed rigorous defense and mitigation strategies, then that is also possible and can be integrated in co-simulation environment. But again, the question will become that how detailed you want, as in terms of behavior model or in terms of representative model. Representative model is something that you exactly know that this is the behavior that I want to model, and I will only model the impact of that. And that's why it's a representative, which is impact is modeled. Not the behavior of the system. And the third, so representative model is, of course, a little bit easier to do. Behavior model depends on that how much detailed behavior you want and how generalized you want. And then third one is emulation, which means that it is more like behaving exactly like the device. Fourth level, which is more tougher, is digital twin, which is the most possible detail. And then something in between is also possible if you, I think even better than digital twin is the actual hardware in the loop, where you replace the whole model with the actual hardware of that device that you want to model in detail. So again, the reason to talk about all of these is setting goals for and deciding that what we want to do with this test bed is very, very important before we start thinking about that how to put my integration between different cyber and physical simulator together. Cyber attack modeling itself, again, depending upon that what you want to model, you need to think about intrusion based, which is, like I said, that you can model representative behavior, which means like circuit breaker open. Now the whole process of that, how attacker will cause the circuit breaker to open. You can model, but you don't need to if you're only looking at the representative model, which is the impact model. If you want to set the power and voltage set point, again, this is a impact versus representative versus actual emulation versus more detailed simulation or more detailed hardware in the loop or digital twin. All those different levels are possible just to do this, right? Then changing of predicted relay is another one. The most suitable will be that there is actual relay and you have certain kind of access to do that. And then there is if you want to model like denial of service, then malware with the virus and worms and Trojan horse, you need to model each of these in details versus behavior. Resource exhaustion, if you want to model, which is kind of a again impact of denial of service, which is overflow buffer, which will result into denial of service or consuming the whole communication bandwidth. Different intrusion incident, again, you can model that also in this test bed. We know about Aurora project, which was only possible with the actual device, and it costed, I would say several thousand or maybe even $1 million. Idaho National Lab that did that attack in 2007. There's a lot of YouTube video. You can search for Aurora attack plus INL, Idaho National Lab, and you'll get that the way that they modeled on the actual generating devices by opening and closing the switch very often. And that resulted into fire or heating of that generator and destroying of that generator. So can I model that in a simulation? Of course, we will not have the similar effect, but it is possible because you're doing some behavior level analysis, and we actually did model this attack a long time back in 2008. After this, they have done that in INL in RTDS, which is a representative modeling of Aurora project. Stuxnet, you can also model, again, only with certain limitations. That was happened in Iran in the nuclear plant. Power plant affected by a virus, which again, it is possible to model. Other one is cyber attack on Ukraine power grid, which you actually saw a quick overview of that we have tried to model in our lab. And each of these modeling will require a specific needs of once I set my goal at what I can do and I trade through with my capability of test bed, will require certain additional modeling effort or simulation effort, or what do you call it. This is always easier to model if you want to model the impact, like loss of load, angle instability. If my simulator in power supports the dynamic, then I can model these, rotor angle instability. If it is only power flow solver, like a MET power, I cannot. But the MET power, the transient part, I can use that instability. Equipment damage is a little bit challenging to model, but excessive torque can be a model, which and with certain assumption we can add that behavior in the modeling tools. A lot of time you also need to think about that the modeling tools, how much control you have. Do you have the ability to modify the internal model of generators? Because without that, I cannot model the excessive torque. Right? So open source, like Mat Power is open source, or MATLAB, you can model your own user-defined model. And so that in RDS and so that in Polarity, there is always a possibility to design your own user-defined model. Some of these will take several days or even a week to model just one generator if you want to represent a user-defined model which is very different than what already exists. If it's a proprietary model, then you cannot do much about that. And then there's just this multiple generator line contingency, which is depending on that the contingency impact is in dynamic or steady state. You can of course model that. Cascading, you can model that like in PowerWorld or others in terms of behavior. And you can also simulate this partial or complete blackout, right? So many different consequences, but typically these are the easiest one to model if you are only looking at the impact, not that how did you lead to uh, that, like the whole blackout that happened. Cyber attack, we already talked about that. If you want to model, and you have to think about different details about starting from vulnerabilities, how to model, how the data will flow, how the attacker will get access from IT to OT. There's a lot of detail on that compared to modeling directly to the impact, which is resulting into a blackout. So again, integrated cyber physical system modeling requires not only thinking about each goals that you want to model, each capability of different software tools that you or hardware tools that you will select to model each of these behavior. And then the next becomes, how do I integrate it? What do you want the goal for integration? So if your goal is dynamic, your delay between the physical system and your cyber system should be 1/10, at least 1/10 of the delay that you're trying to model in cyber. So if you're trying to model a data packet delay of, let's say, 0.1 second, then your integration of cyber versus physical should be not more than 0.01 millisecond, because if it's more than that, it will impact your ability to model that communication delays in the cyber system. So integration, there are multiple things important. One is that noise, that how much noise is traveling between your cyber and physical system interface. Next, what is important is synchronization. What time clock was used in the cyber system, what was used in the physical system. If you're using most of the steady state solver, then you're using the computer clock. But if you're using the real-time modeling technique, you can actually use the GPS to synchronize it, or another internal simulator clock to synchronize it. So accuracy of the integration depends on behavior that you want to model, how much noise, how much delay in cyber and physical interaction is, and then synchronization. But in each of these, you have to develop the cyber model or ICT model, right? You have to develop the power grid model and then integrate it together with the control hierarchy that you have modeled. If you're trying to do the dynamics of power grid, it is more tricky because, of course, you need a system in the power grid simulator that can do the dynamics. And then all the data infrastructure, which is providing the data at faster time scale, because dynamics is faster time scale. And even in dynamics, there are different time scale that we're trying to model, right? If you are dealing with, let's say, transient stability, we are talking about, in milliseconds. If you're dealing with protection, we are also talking about millisecond. If you're dealing with electromechanical interaction, which will like torsional impact, or which will change the torque in the because you're increasing the load, you're slightly dealing with a little bit lower than a few milliseconds. Then once you get to the electromagnetic behavior, then you are talking about really a fraction of millisecond, right? So you get to the microsecond. If you are talking about switching behavior of the power electronics, then also you're talking about nanosecond to microsecond, which is a faster switching phenomena. Now, all these detail and each device is also important that it should represent all the dynamic behavior that you want for the whole system to behave, right? Because when you are saying that integrate power grid model with the cyber model, each system here, power grid itself, is a multiple subsystem. Each subsystem, like just a generator, is also a system of system, which means that there is a generator model with a lot of these components. There is a field winding, which is a control, and then there is a governor control, which basically does the real power control. And then you want to put on the top of that SCADA for the generator right there. Some are being used locally, and some are going out of that generating substation. So a lot of these details will decide, will depends on that what is your goal to use that model. And then comes the CPS tool, which is for communication performance, which is again important if you're trying to model the delay behavior, which is either happening because of cyber failures, or even bandwidth has been utilized fully, so there will be delay, or because of some attack, right? So if we just talked about the attack, like overflow buffers are consuming the communication bandwidth because of some kind of attack, will result into a delay, right? So all these delay, which is a communication performance, will either because of cyber failures or because of the attack, it need to be modeled. And that can be done again in the same level that we have been talking about: behavior-based, representation-based, and then the simulation-based and emulation-based, and then digital twin-based and hardware-in-the-loop-based, right? All these things can be modeled. And then comes the more detail of cybersecurity assessment in co-simulation environment, which is so this is the third thing, right? So don't think that when we say model the cyber system, it already include all of these detail about the communication, about the data packets, about the cybersecurity attack. Each of these need to be modeled separately. So this is also a system of system modeling with a different component, and you'll see some examples very soon. So modeling the cyber attack and assessing the cyber CPS security will be third layer that you need to simulate or emulate or model representative behavior, and then impact analysis, which if it's going to give you a true behavior of cyber attack on the power grid, then all these three layers has to be modeled in that detail. You can also have some compute impact indices and attack efficiency if you want to do that. Now, just looking at this, your physical versus cyber interaction, cyber is also in the same way like a physical system. You have to think about, are you modeling the distribution operation or transmission or RTO ISO operation, interaction between that. Then there is a whole cyber, which is actual only cyber, is a market behavior, right? Market does not directly relate to any hardware. It is all data-based market behavior simulation. And so this is all numerical analysis, but requires a lot of data from the bidder, from the aggregator, from the wholesaler, and if you want to model that, because there's attack possible here too, we have to think about it. And then if you want to model the attack, which is originating from the service provider, you have to also model third-party provider, which is the same access point the attacker will use to get into this whole system, right? So it's all about how again, going back to the goals and how much realistic simulation you want, how much real you want to make it to the real system. And it turns out that it's not possible to model everything in the cyber system, and no one in the world has ability to do the cyber physical simulation with all the details for everything. It's just not possible, right? Because the resources that you'll need will turns into several million, and even I mean, when we say several million, we're talking about hundreds of millions dollar to simulate all of these, with going from nanosecond time scale to several minutes to hours, and then sometime days, if you want to study what happened in, like, let's say, Ukraine cyber attack, because the attacker were there for several months before they launch attack. So if you want to model that phenomena, you're talking about years of simulation over time. And then you want to model all this generator in detail with all the control. You want to model the TND interfacing, which is also very tricky. And you want to model the customers and DERs with all the control and all the data flow and the communication link and each of these devices which does that. Which means if we cannot do everything, we have to choose what is our goal. We want to model the attack originated from the third party access point. Okay, we will do that. It will take some effort, but we can do that. You want to only model the distribution system and service provider integration, or TND integration first, or RTU integration, or market, or where you want to focus and what behavior you want to model. So these are the right questions to ask before we start the cyber physical simulation. And then each of these is a lot of effort. If you want to do it accurately and seriously, it does take several months to year just to model the this effect in detail. In the end, it's all about that. What was our goal, and what is our budget to afford which part of the system behavior I want to model. So I'll give you 4 different examples. I mean, of course, we have also done the cyber physical simulation to behave and model different things depending on that what project we are trying to work on and what is the final goal. So in this one, our goal was to only focus on PMU based control and operation. And because it's a PMU, so we do want dynamics, and we want detailed dynamics. If I use the steady state behavior model, it will not represent the PMU, basically the CT and PT current that is needed by PMU. And then PMU itself has so many different blocks, right? So it has in PMU, you have starting from the CT and PT, you have to filter it. You have to first, eliminate the noise, then you have to filter it. And then the filtering is done twice. Then there is a whole synchrophase estimation process. And then if the synchronization with the GPS clock is missing or removed, then there's a PLL in the PMU, which will allow for a certain time, but after that it will be drifting. So just one sensor has a lot of details. And we had choice that either we model it or we just buy actual hardware and put it here, right? So we went with that actual hardware and then integrate it with RTDS. So we do need dynamic simulation. So RTDS was, of course, one of the possible way to do that, which comes with all the dynamic behavior of the power system model. Then we can do the actual PMU, actual PDC with the database to analyze all the system information about the PMU and PDC flow, and with the multiple PMUs. And maybe if you're modeling multiple substation, then multiple PDC at substation, and then another substation, and another control room which will have a super PDC. And then all this control center node interface. which we used DITERLab, which was actual emulation using, I don't remember that how many cores we used, but it was hundreds of core. DITERLab is one of the communication emulator which came from California in one of the university, and actually it was done because of the military, and it was one of the, I would say, one of the best. It's not a simulation; it's an actual emulation, which means an actual server which is communicating with, and we got those node installed in our lab. And then you have this application running on the control center, which is OpenPDC or SuperPDC, and then we had our own tool for voltage stability monitoring, which that was a reason that we wanted to check that how does it respond with the different cyber failure of GPS failure or communication link failure, and what is the performance of this. Other than this, we also wanted to check on the remedial action scheme, which is based on the PMUs. So that was the region, that was the goal we had in this test bed. And then from here, we went into more detail. So first part was that if you are getting the SCADA data and the PDC data, these are the two different one. So CT and PT, of course, you can model in RTDS, which allows it and get into the SCADA. PDC is getting from PMU, which we had actual hardware. And then we wanted to deliver this set of data to the, your application HMI, which is running in the control room. So we use this OPC protocol to do that, and then all this data translation need to be done so that it can understand the OPC input, and it can your application can understand the OPC output, and then there has to be some database for archival so that we can analyze the data later. And then we continued the interface with network simulator. So you saw that there was one which is a DITERLab, which is directly takes this interface is important, right? But we were not locked only for DITERLab, so you can you have a choice. This is hardware. This is also RTDS simulator. Here I can change DITERLab to NS3 to Mininet to all the different simulator depending on limitation. So DITERLab, if you have only few cores, if you have 2 cores, you cannot model a bigger system. Of course, in the USC, which is University of Southern California, they have hundreds of DITERLab node, and they can model a bigger system. With certain limitation, you can have thousands, and you can model a more bigger system, but still there will be a limitation that how much you can do. With NS3, which was actually simulator at that time, and it was evolving into emulator. So we were one of the first to use that to make a emulator. So there is actual data flow, and this was done long time back. So now we got this actual hardware, which is talking with the PDC, which is a software interface. And then we got database at each substation, and this is one substation, this is another substation, and several like that. And then this is the final control room, and all of these has to talk to NS3. Now NS3 has to take all this data in and has to do the actual communication behavior between PMU and PDC, and between PDC and the control room. But that's not how NS3 is designed, right? So there's a single interface and single interface out. So to represent that, we had to do this tab device into the simulation so that we can model each of these, independent. Even though we had hardware, it will not directly talk to NS3. So we have to build this bridge, Linux bridge, and then have each of these devices again represented so that it can model the one-to-one communication within that. It's not ideal, but this is how NS3 worked at that time, right? So with Linux bridge, this is a single bridge to take all the data in. And each of these are again represented in the simulation by type device 1, type device 2, type device 3, and how many type devices you want. And then using that, I was able to, we were able to simulate any delays that can happen between PMU to PDC, between PDC to control room, and even the how it will impact my application, which is either voltage stability based on PMU or remedial action scheme, which installed at 3 substations. So all of these could have been modeled with actual NS3 emulator. Then let's talk about second example, which is actually using the MATLAB for cyber system simulation, which was and then this was also done long back by another colleague of mine. And then they use Dick Silent Power Factory because for power system simulation it can model the dynamic simulation. And then SCADA software for control room was used as a as actual which is Siemens here, Spectrum Power. And then OPC protocol was used with actual Metricon OPC server. They interact with the 10 millisecond rate that was it was decided, and the system used to synchronize simulation, right? So here you have again Dick Silent Power Factory modeling the power system layer, right? So this is the power system layer, and then you got to have OPC cloud so that it can give you the voltage and current that you want into the server, and from the server, MATLAB was used to model the communication network, with all the node in detail. We'll talk about a little bit more detail. It has to be an OPC client, and there will be another OPC client which is talking with another OPC server, which is delivering the data and taking the data from the SCADA, and which is kind of mimicking the delivering to the EMS, right, or your application. This also has to have OPC client and then state control variables. So now in this integration, you got power system simulator, you got your MATLAB Simulink and sim events for the cyber simulator. Then you got your SCADA with Siemens SICA. And then this is working as an interface between all of these, right, with the OPC server. So this core simulation must integrate time domain simulation for power system dynamics. It should be able to do the discrete event simulation with MATLAB Simulink. And again, cyber is always discrete, typically. And then it has multiple servers and clients and communication protocol, right? So if you go into a little bit more detail, then you got power system layer model, which you need to choose a system, and then the time scale that you're looking at. Then it has to represent multiple substation MATLAB, which is ICT model, which has different details like engine workstation, station HMI, web HMI, remote terminal unit, IEDs. Everything needs to be modeled in the MATLAB. And then control center cyber also need to be modeled in the same way with a lot of details. And then finally, a transmission system operator layer need to be modeled as a SCADA delivery point and EMS, right? So a lot of these communication, which include standby, which is basically the secondary control center as a backup control center, and then also the actual control center. So a lot of details has been modeled in this. And power system layer was chosen with the Dick Silent. Basically, as you can see, the different substation need to be also decided so that you can represent that in the cyber layer. And as you model the power system, then it will that internally it's solving basically your differential algebraic equation and to do the simulation. You need to decide on a state and control variable that you want to sample and measure, right? So all this sensing is all in power layer. There's no CTPT model externally. So it is modeling the power system, it is modeling the sensing layer, it is modeling the control layer, and then interface with the cyber layer. And then again, you got the substation level at cyber, in cyber system layer. You got control center layer, and you got transmission operator layer. So all of these now has to be represented in the MATLAB and also interfacing with different layers, right? There are so many different components that need to be modeled in MATLAB. So in MATLAB, this was the fundamental way to do that. That you want delay to be modeled, and that for that one, you need to do the FIFO queue packets, ICT buffer, arrival rate, all these kind of things, and then you need to do the processing delay, right? So that need to be modeled, and then you need to do the how much data is coming out. So data in, data out, would all need to be modeled at the each step when the data hops from the point A to point B. So ICT model as a queuing system, that's what you actually happen in the communication. If you have taken a communication courses, this is one of the thing, queuing system that happens, and then delay, right? And then the ICT simulation model, which or these basically a lot of these component has to be put together to form the whole cyber system. Again, using the MATLAB Simulink and sim events, right? This is one way of doing that. And this is generic because it can stack together. And then you also model the substation ICT model. So you have to model the bay level local area network. You have to model the connection with IEDs and RTUs of that network. You have to model the RTU enable communication, and then local area network at station level with Ethernet, and all of this, right? So this connection need to be modeled, that, and each of these, how it is represented in your model. The substation model, as you can see, that each substation is quite detailed with sensing, with same model of queuing and delays and attributes, and then same thing for actuator, and then everything in between, which is connection from each of these block is representing this one in detail with each port, and then path combiner, and then IED simulation model, which is again queuing and serving server model, and then finally the actuator, which is going to give a signal to the power. So again, this is all about how much detail you want to model, and this seems pretty detailed. And then all the RTU and other things that you want to represent here. You can also model router and firewall using the same thing. Once you understand that how firewall works, right? You got this basic block of queuing and delay, which is FIFO queue and all those things, and then each block, how does the path combiner and control center and RTU and substation, all of these need to know the detail that how it's connected before we model it. And then same thing, like a substation, we have to model the control center with more number of devices. It still has to have a system server, application server, HMI, synchronization system, and then every other interface that it's talking to. And finally, we get this to transmission operator ICT model, which will be the next layer to model with more number of application. And you can also have a cybersecurity application like a defense and monitoring mechanism if you want to model that at this layer. We have to have certain historian, market system servers, all of these things like basic security, firewall, RTU servers also modeled. We can have a TSO console model, which is set of again similar data coming from the power layer and exchange through CPS layer, and then all where it need to be delivered, right? So all these need to be known, and then only you can model it. And then finally, if you want to model the cyber attacks, it can be also done. Going back to the same layer, that here is the power system model with interface, OPC server, cyber layer, MATLAB, which we just talked about, each of these details, and then your final SCADA and EMS system, and and then if you want to model this communication security, you can simulate it here. And if you want to look at the SCADA performance because of the attack, we can actually get the result from here. How does it impact the real-time SCADA and EMS? We can see it because we modeled the attack here. And then cyber attacks can happen either in this layer or it can happen in the software layer, which is here. And then impact, we want to see it in this one, right? So these are possible, again, once we model it. So cyber attacks can be modeled using this CPS tool. We can model general service attack by flooding the queues, right? Because we already modeled queuing in using this the whole system. And man-in-the-middle attack can be modeled by this capturing and modifying the packets, right? Because we are the one who are sending the data packet from here to here, right? So if you want to put a man-in-the-middle attack here, we just need to take the data, modify it, and deliver it here, or from here to here, or from here to here, whichever we want to model. Unauthorized access can also be modeled, such as RTU and IDs, because we have the detailed model of RTUs and IDs using the same building block of cyber system. If you want to model the attack graph, like one device to another device, then another device, that can also be modeled using the same thing because we do have a detailed cyber network. And where the attacker wants to reach, of course, that goal need to be decided, and then we can also do that. All of these ICTs that we have modeled are vulnerable to cyber attack and can be modeled using this test bed. And we can, once we understand the vulnerability in each, which is representative model, we can also do the penetration testing kind of vulnerability and penetration times they can. So if you want to model the graph, this is how it will look like, because we have this all connection model. So workstation remote access that leads to the communication server attack, and that leads to the RTU attack. This is one path. It can also come from the router firewall being compromised, and then communication server 2 to the RTU. Or it can come from the web HMI to the communication server 1 and then to the RTU, because RTU is connected with these two servers. HMI 2, HMI 1 will also lead to the communication server and then to RTU. So multiple path, and we can, because delay is a model and queuing is model, so we can all see that. Different cyber intrusion scenario can be modeled using this test bed. So outside substation network, it's originating or inside or various subnetwork location. We can model this. What path it's taking, because we have modeled the communication in detail, we can model that also. And where it's ending, right? And then all the method differently used to represent that attack with different ways, right? So as you see that there's not one way of doing things. Everything has a limitation, and everything has a ability to model with certain effort, right? So real time, this is not real time, which is a MATLAB, and you can analyze and model things in multiple different ways. Like I said, again, repeating the same information because it's very important that we need to understand that this is not a digital twin model, because you have in this model you cannot represent a digital twin because there's no hardware which can take the data in from the real system device, right? So it's not digital twin. It is doing the representative behavior, it is doing the impact analysis, and it is doing the emulation, because there is a data packet that is actually flowing between the different blocks that you have modeled. So using that, it is possible to do certain analysis, and then all these simulation result will tell you cyber attack scenarios that you want to model, including unauthorized access. And here, that one example we took, the target was substation RTU, so it can be used to control something. We can model the attack path. You can model the vulnerability exploitation and security control if you have modeled that in the system, and different cyber attack scenarios, which is substation, workstation, communication server, RTUs, and unauthorized access, which will result into the attack. You can also model scenario like cyber attack at substation 3, which again looks at the path vulnerabilities, which one is a certain assumption that which one is more compromised, and then you can compute overall success rate for a cyber attack, right? Um, and what will be the impact on this, right? So don't go into detail of these, but because this is just example, right? And then also, if you have model which is possible with dig silent, the tap position for the transformer can be modeled and modified using the attack, and all the dynamics which can be also modeled with the cybersecurity. You can look at the dynamic responses in terms of impact on the frequency, which is showing the frequency impact, and you can look at the voltage and other things too, right? So this is voltages at different. This is impact modeling, and then active power. Now we talked about two examples. We are not comparing direct to direct because we had a different goals to model and different limitations. If when the MATLAB was done, there was not many cyber emulator or simulator at that time. I'm talking about 20 years before. When we did this NS3, then NS3 simulator was available, but not much emulator, but we helped kind of to make it emulator, right? So resources are available, and now we have like tens of different cyber simulator, right? And so that physical simulator too. So in this one, which is example 3, we want to do electromechanical simulation with, of course, which is dynamic between the distribution system now, so that is focused now, and Mininet, because we wanted to look at distributed optimization application in a microgrid. That was the reason that we came up with this simulator. And here we are using Mininet. And we wanted to model the microgrid, all the DRs. This was a military microgrid, so they were interested that if a cyber attack happens, how to design my cyber and how to design my physical system that I can increase my resilience, I can survive. And for that one, distributed control is typically better, because even if you compromise one, there's no centralized here. So you compromise one, others will keep working after isolating the compromised one. And that was the main motivation for us to work on this kind of simulation, when you can do the distribution system on OpenDSS or GridLab-D or even MatPower. If you modify the simulation or MatPower to represent your distribution system, or you can use MatPower for transmission, but it will not represent the dynamic behavior unless you use that functional block. And then you need a Mininet, and then you need an interface, which is a Python wrapper here. DR were modeled in detail. We had even a protocol model for DR communication, and then we are able to launch a lot of different attack. You can do the of course the control layer attack, because there's a DRs connected and model in detail here at each node. You can do DR cyber attack. You can look at the communication link and how it will be impacted with this model. So again, another example of doing things that what we wanted to do. The fourth one, which is the last one I'm going to talk about, we wanted to look at human operator behavior, okay, and how these operators will respond to if there is attack on the power grid. So we wanted details in power system simulation, and that's why you're using electromagnetic simulation. Real hardware in the loop. We wanted to model switching as much as detail possible in the DERs, so that's why Typhoon. and all interface together, feeding the data to a server with the communication model in NS3 and a lot of these defense there. So we model the software-defined networking, we model the Splunk, which is going to look at all the cyber data logging and monitor it. You can put a lot of your logic in the Splunk server. Snart, which is another kind of monitoring for cyber networking. PingThings, which is a company that came out of University of California, Berkeley, but now it is basically can process the data database really, really well with the SCADA and with PMUs, whatever you want, and fetch the data in like a microsecond, right? So really, really fast. PingThing is database archival and visualization software. We also wanted to look at the operator response. So we're looking at the cognitive behavior, and that's why we had this human factor sensor to look at how stressed they are when they're making a decision with a cyber attack. We want to track their eyes, that where they are looking at, and we want to do some more testing for the cognitive behavior, so we can measure their cognitive flexibility, and that's why we need to model the control room environment, right? Again, this one has a very specific requirement of this test bed where transmission system need to be modeled with detail of DERs, because that's where the attack can originate, with the generator, which the attack can generate, with the tied relays and PMUs, but it also has a limitation. We cannot model a big system here, right? So we were less than 100 bus system. We cannot model all the DRs in detail because this Typhoon can only represent certain batteries and certain distributed generator like solar. And NS3 is used, which is again has the single layer of interface. So it is not going to represent the true behavior of the network that we want to model, but it can be used for access to different relays, because with the hardware and PMUs and RTAC and all those things, which is here with the GPS synchronized. So a lot of details, but also some, limitations of that. So what I want to emphasize that your test bed, we talked about 4 different test bed. We do have more, and that will be the next thing that you'll be looking at in more detail about Mininet and NS3, and then how do you choose your cyber simulator. But any cyber physical simulator that you want to do, your goal is important. Knowing the limitation is important, because physical simulator, as soon as you choose that, you know what is the limitation of that. Cyber simulator, as soon as you choose, you know the limitation of that. Interfacing these two, everywhere you'll see that there's interface. Here it's NS3, and then the way we interface. In earlier one, you saw that there's a Python wrapper. In before that, this simulator, you saw there is a OPC server, which is basically doing the sensing and control. And then before that, you saw this this interface, which is Linux operating system bridge with NS3, and all these different interface, which is either hardware or Ethernet. So interfacing, minimizing the delay, understanding the accuracy, synchronization is all important in any code simulation. And once you understand your limitation, you will design the use cases in such a way that what can be studied using this testbed and what cannot be. So it's an iterative process, but start with the goal and then iterate with that. So let me look at some questions here, and then we can go to maybe take a few minutes break, and then Dr. Kasmas will talk about how to model the cyber system and do some, show some demo. Okay. So next one, the question I see is that when modeling the digital twin, do we need to model the digital and physical grids separately? And how these two grids can be used for anomaly detection and other decision-making control. So, again, let's start with the goal. So when we model a digital twin, a digital twin does not mean that everything that real device is doing, you're going to do in digital twin. You get to decide that. So digital twin is modeling a certain behavior. Digital twin has some certain requirement, which is what were you trying to model? It should be exactly the same what happens in the field. Second, there has to be some data flow from a physical system, physical device, or physical system that you're trying to model to your model, so that you are adjusting in real time as it is being adjusted in the field, right? So these two are the requirement. Now, when you say the digital twin, you get to decide that what behavior you want to model. You want to model steady state power, you want to model the communication delays, you want to model the cyber attack, you want to model the dynamic behavior of the model. You have to put the boundary there that my digital twin is for cyber physical behavior versus my digital twin is for the physical system behavior, and what kind of behavior. So once you set those up, then you will have to find a way to bring the real data from the actual device that you are trying to model the behavior into your and then you need to use that data to make your model behave like a real system, which was your goal, right? So again, you get to decide that you want to model digital system or physical, or you want to represent both, right? Of course, if you want to represent both and with all the details, then it will be digital twin for all the different possible behavior that device can represent. So you can decide on that, and how these grids can be used for anomaly detection and other decision making control. So let me like let's say South Korea. So South Korea grid is not very big, right? I mean, compared to US grid or grid in other part of the world. And because it is not, so they can model the whole system, at least the physical system part, into RTDS, and that's what they have. I'm not sure if they're still using it, but they can do it. And now, if anything is happening in the real field, it should be represented into RTDS if they have modeled it correctly. If the behavior in the model, which is digital twin, is not representing the same thing what is happening in the field, it means that either your model is wrong, or there is something happening in the real field which is unexpected. And unexpected relates to the anomaly, right? So that's how you can use that for anomaly detection. Decision making, yes, if you can, there's something called faster than real time. If your decision making is done in 10 seconds, right? So again, decision making for what? If it's a transient stability control, which is going to happen in few cycles, and you cannot simulate that in your digital twin, then you cannot make a digital decision making for that, because you need faster simulation and control action output, which is not there in your digital twin. If it is a voltage stability control, which you have a several seconds, even a minute for that, that is definitely possible if you have a digital twin and you can simulate there and can generate your decision making in your digital twin, and everything by taking that control, it works as it should be, because it's faster than real time. Your real time was several seconds, and you're able to simulate that in 5 seconds, and requirement is 10 seconds, and you have 5 seconds still left where you can look at the impact on the system and solve the problem. So now you got decision making control in your digital twin, which can be implemented in real field, which is validated because your digital twin was representing the behavior actually that you wanted. Next one, when talking about DOS attack, denial of service attack, do we consider attack that makes packet delay, corruption, or reorder? Yeah. So again, we get to decide that how much detail we want, right? If you want behavior model, then you model the impact. If you want to do the behavior of DOS attack, the process, then you have to do the packet delay, corruption, reorder, all those kind of things. going back to that, it's all about that what we want to model and how much detail we want to show that and how much capability and budget we have. It's all about resources, because if you want to model a super digital twin which can represent everything, it requires several $100 million and a couple of years to do the actual grid. If you want to do the one behavior, then you can do that too, which will be much cheaper, and but certain limitations. How can we model the FDIA, which is in on the communication channel? I think it will be probably more clear once we talk about more detail about Cyber Simulator. But for FDIA, again, you will think in the same way that am I going to model the impact or behavior or a detail of the whole process? And once we know that, we can do that in how it originated, because FDIA does not originate only in the communication channel. It can be at the sensing level too, and it can be at the last, which is the control level. That can also there, right? Because you're only trying to falsify the data. So man in the middle attack will make it happen at any different point, or even the false data injection can happen with spoofing, right? So the multiple way to do that, because FDIA is only the impact on the system, and the process. You need to think about it, how you want to model it. How can we validate the developed CPS against various cyber attack vulnerabilities? So validation again has to start with the goal of what we want to validate, right? And then what is the benchmark? Any validation is about benchmark. And when we model the CPS with the cyber attack vulnerabilities, unfortunately, there's no way that we can get the benchmark from the real grid, because we can't attack the real grid. So it has to be done indirectly. So any validation, you have to think about that. What do you expect it to do? And is it doing the same thing or not? And it is doing repeatedly the same thing. So if you use the test bed and you model or you simulate or you emulate with the attack, it should give you the same response if everything else is same. Of course, if you change the environment, if you change the simulation operation point, then it will give you a different result. But if you keep the other things same, that's another way to do the validation. Vulnerabilities, it's assumption, right? Because vulnerability only will come with the real hardware, which actually has that vulnerabilities that you want to model and simulate. With the real hardware, you can, of course, validate there too, and that could be another benchmarking, because some part of the CPS simulation or emulation has been replaced with the real hardware, and you can model that hardware in your system, and then you can compare that if I do that in real hardware, and again everything else is all the possible error has been taken and considered, then my real hardware in the loop and my model in the loop, if both are matching, then that's how you declare that my model is same behavior as a real hardware. So a lot of different ways to do that validation once we know the goal and once we have the resources. Is there any Python library for cyber physical modeling used by researchers? There are, right? And in terms of all the names, I don't think that, we can probably look at, but like none of them is going to be perfect, right? So Python for power, there is a PyPower and so many different software for the power system modeling, but it comes with its own limitation depending on that, what you're looking for, steady state versus transient versus dynamic versus, all your more detail about protection and those kind of control, right, which is more finer time scale. In terms of cyber, I'm not actually recall any. What will be the name for that? Like a Pi Power or Pi DSS is for power. Uh, but I'm sure that someone must have developed for the cyber with certain limitation, and then the Python wrapper, is needed. The interface is needed. You will get to again offline, so there will be some limitation on that, but it is definitely possible. Which I don't recall that. There's nothing which is very common and very popular, so that's why I don't recall. But I'm sure that there will be something, just like for physical system we have, there should be something for the cyber too. How can ICT model and synchronized file data work together to improve the monitoring and maintenance of electrical power system? So this is something that already happening, right? So if you have a PMU installed, you will put in the field the ICT network to feed the data, right? Yeah. Once we want to model it, then it depends on that how much detail we are modeling for the ICT model, which we already talked about in detail. And then PMU application is the one which will decide that how do we monitor the system and what we are trying to monitor. Maintenance of electric power system is totally different problem, and where the PMU installed and how close it to the asset, because we actually maintain the assets, which is either generator or even the CT and PT is assets, right? So PMU will give the information. There are a lot of use cases which has been presented in NASP. You can actually look for NASP, like a keyword on Google, and you'll get a lot of different application and the process of doing the maintenance of electrical power system assets using the phasor measurement data. Again, that is that will be different. That how do I monitor and maintain transformer versus monitor and maintain current transformer or actually the generator. So I think that answer will be pretty long on this because there are so many different ways to do the different assets. And then I see how much time does the system take to simulate the model in example 2. So it was mentioned it was 10 seconds, right? So we had the goal of 10 milliseconds, right? Okay, and that means that everything should be done in 10 milliseconds to do that, and this is fast enough because we are only modeling a simple queuing and delays, right? If something is delayed and we want that data to be delayed beyond 10 milliseconds, then that's what will be modeled there too. Does co-simulation means connecting power system simulation and network simulator? Yes, yeah. So that's what co-simulation means, that because these are two different simulators, so it is representing and it's modeling and simulating its own, but it is doing at the same time scale, and that's why it's a co-simulation. If the time scale could be two different time steps, that's also possible because one runs faster and another one slower. But as long as we are aware, the co-simulation is still possible, and because in the real system also it's happening in the same way, that one is running faster and another one is running slower. All right, so we'll stop here. Maybe take 2 to 3 minutes break, and then Dr. Cosmos will talk about system in cyber simulation, and then show you some demonstration for Mininet. And then he will continue tomorrow to talk about, so we talked about testbed and then some hands-on demo today. And then the next thing is data. But before data, it's important that how do you process the data? So it will be generalized AI introduction, and then later it will be about cyber physical simulator giving you data, which is kind of embedded everywhere. We are generating a data. Data need to be processed and then used for detection of anomaly, classification, and root cause, and then once we classify as a cyber attack versus cyber failure versus physical system failure, then only we can take action on that. So that will be the next 2 days of work before we kind of wrap up on third day, on fourth day actually, right? So that'll be Thursday, and then we'll continue with the EMS, and then Dr. Shukla will be talking. Okay, so I know that Dr. Cosmas is already here, but we can take a few minutes break and then he can start.
Sure, sir.
All right, sounds good. Thanks.